So now we have IPv4, we have IPv6, and I told you that we do not have 100% IPv6, we have to migrate somehow. So how can those protocols coexist? Well, this will, I guess, be the case for the next 10, 20, whatever years. The point is we cannot simply switch to version 6 overnight. Just say, okay, from next year on, only version 6. Would be nice, but doesn't work. The point is we have to update many protocol stacks. Okay, operating systems, done. They support it already. Also in the routers, okay, done. DNS supports it. Applications, well, not all of them. Services, yeah, many of them. But administrators, they need tutorials, they have to learn how this works, etc., etc. So for some time we will have both, and this is a lot of work. So for some time we will use both IP variants and use them in parallel. So we have some problems. For example, we cannot simply go for v6. Some of the socket APIs, they are not IP version agnostic. So applications, they simply assumed we have version 4. So sometimes even hard-coded addresses or the formats of addresses. So now we have new data structures, we need them. And so that's a problem we have to deal with. So we need incremental deployment. And the question is, how will to enable, well, the new IPv6 based host to communicate if the network is only version 4. So can we do this? How can we have both at the same time? How do we port? How do we migrate? And porting basically is we make the application ready for IPv6. So implement the new data structures, have socket APIs that are now protocol version agnostic, and also migration. What is kind of a seamless step-by-step transition from 4 to 6? We use both in parallel, and there I will show you there are different ways how we can do this: dual stack, tunneling, protocol translation, etc. So making applications IPv6 ready, that means not only version 4, so it's different. But now we have to check source codes, binaries, sometimes if they're IPv6 compatible. Sometimes there are certain fields, data structures that can only handle the short 32-bit addresses. Now we have 128 bits. So there are new functions that have to be supported: address conversion, name to address translation. We heard already something about DNS and the mapping, and this now also has to be implemented for v6. The protocols resolvers have to return addresses v6 and v4 or v4. So there has to be done a lot, new address structures, and so on and so on. So we have to say today, 23, 24, almost all standard applications, they are already ported. So that's not the point. So, but it was a long way to go from the mid-90s, well, almost 30 years until now everything is v6, but still we have many v4. So just to give you an example about the data structures, address conversion functions, name to address functions, you see there's get host by name, get host by address, for example, for v4. And that had to be changed, or data structures had to be changed, socket address, etc. Because in former times, if you talked about internet, it was automatically IP version 4. So it was not IP version agnostic because no one thought of, oh, there will be a new version. So the original socket APIs, the APIs, they prevented really this fast deployment. So we had to update everything. This was done, so we have the new functions now. Okay, what else? We have to migrate. Migration, that takes time. So we use several technologies in parallel. So quite important, dual stack. So we have the coexistence of version 4 and version 6 on the same device and subnets. I already showed you an example for DSL router that says, okay, I've got following IP version 4 address and this is my IP version 6 address and I can handle both. That does not mean that your ISP also fully supports everything on IP version 6, but as you saw in the example, this happens. So how can we connect IP version 6 regions? So in the beginning, maybe some of the universities had IP version 6 and then more and more providers. So we had to be able to connect these regions, IP version 6 regions, over version 4 regions. And then there's also technology, I will come back in the context of IP version 4, called NAT, Network Address Translator. And this enables IP version 6 devices to speak with version 4 devices. But what is quite common today is that we have the dual stack so that devices can handle basically both. So there are different ways of how we can migrate. So dual stack. Dual stack, well, we use IP version 4 until we really fully activate version 6. And from then on, we use version 6. And there's even a way how devices can keep their version 4 addresses in version 6. So it can be embedded. And then the applications or the libraries, they pick the right IP version, depending, for example, on the DNS answer. So if DNS, you ask for address of a name of a server, etc., and then you get the DNS answer. We know how this works. Then the answer includes that, oh, I prefer version 6, or I receive version 6 IP packets. Then I answer using version 6. So this is why the devices have these two stacks, one classical stack. So I will come to layer 4 in the next chapter. Here layer 3, and with some supplementary protocols, ICMP, and alternatively the version 6 stack. So we can do this dual stack operation, we can do this for indefinite time, and then we can step by step port the applications. But the point is we have to use IP version 4 NAT. I will come back to NAT. Why? Because as long as we use IP version 4 in parallel, we need an IP version 4 address. But there are no more IP version 4 addresses. And one way of dealing with scarce addresses is using network address translation. Okay, and then, well, there could be some problems in configuration. So DNS returns version 4 and version 6 addresses. Now the application picks version 4, but maybe version 4 is already disabled, so you have to make this consistent, etc. So that works. And in the following, I will just give you some examples of how this can be done. And if you're interested, please have a closer look then. There are enough pointers to the literature where you find more information. Okay, for example, there's the dual stack Lite, there's a RFC. And the idea there is, because we don't have enough public IP addresses, we don't use the public ones at the customer. And so what can we do? The system, so at home, uses, as we see here, a private IP address. So private IP address, for example, 10.0 or 192.168, etc., etc. So private IP address, and sends this then to the home gateway. Gateway, that basically router with some added functionality, that then creates a tunnel and says, okay, I have a provider, service provider, that offers already IP version 6. And here I can use the IP version 6 address to send the packets, the original packets with the private IP addresses across this tunnel to the then to the other side. And there, on the other side, because I've got a private IP address which is not routable in the internet, I have to do something. I will give you some more details about this later in a special subsection. I have to do a network address translation, and I will translate then the private address in something that is routable. So initially I had the private address, you see here, the private source address, which is then translated in something that can be routed. Destination address is the same. And then here, classical old IP version 4 internet, there could be a server or whatever, then operating on IP version 4 answering. So you see, this basically supports that many customers can share a single globally unique IP version 4 address. So this is our 129, etc. That's the global unique IP address. And all the customers have their private addresses. So that's one of the ideas. And the provider of the network can have already an IP version 6 network. We use IP version 6 addresses. But the customers, well, they can have their private IP version 4 addresses, and also some service providers, for example, could still have their IP version 4 addresses. So you see, we can mix different techniques to support both worlds at the same time. So there are many ways of using these tunnels, and tunnels are a simple thing. I mean, tunnels, we use them quite often. A tunnel is nothing but you encapsulate one packet, giving it a new envelope, new addresses on the outside. So you take a letter and put it in a new envelope and write a new source and destination address on it. And you even can take this now and put it into yet another envelope. So you can have tunnels of tunnels and several time encapsulation. Okay, this increases the packet size, but that's a different story. So tunnels can help, and you can create these tunnels. And there are many different ways of what you can do and how you can do this. And there are just some pointers what you can look up, how to build these different types of tunnels, how you convert 6 to 4, so IP version 6 to version 4, etc. So even you can run your IP version 6 VPN over IP version 4, etc. So tunnels are just a tool where you can say, okay, there's some other technology and I have to transport something in my format across this other technology. So that's the idea of a tunnel when you encapsulate something. So example showing this, how this can be done. So here in this setting, we have two IP version 6 networks. As I said in the very beginning, for example, universities, you had 2 of them, and there people tried IP version 6. But the classical internet, that was mostly IP version 4. Okay? That means somehow the routers here has to do something. And that's exactly where you start the tunnel, where you encapsulate incoming packets from this nice IP version 6 network into something, okay, older technology, into a IP version 4 network. And the destination in this case is also then, well, somehow you have to find your path, IP version 4, and then you end up at a router that can also handle this. So you have your packets, classical payload IP version 6 header, and this has to be transported, but cannot this way because it's an IP version 4 internet, so the provider doesn't support it. And then you use an IP version 4 header, encapsulate everything, and you decapsulate at the router on the other side. So router 2 decapsulates, router 1 encapsulates. So that is one way, and this basically establishes a tunnel between the two routers by encapsulating the packets. And this means both IPv6 networks, they can communicate with each other. There's a lot of overhead. Yeah, you have two headers in a packet, but you do not lose any information. So this is a very general concept. We use it for multicasting, VPNs, and pack a whole packet as it is into a new packet, a different protocol. So that's our tunnel. In red or in blue, that's the tunnel. So that's one scenario where we have two IPv6, I would say, islands connected over a internet that supports IPv4. There are also other scenarios where we have your IPv6 islands, but at least you have IPv6 backbones. So there are also these structures where I say, okay, again, a pointer where you can have some more information about this, how routing IPv6 over version 4 works. So with different tunnels. And the problem is, well, yeah, how to pick the tunnel. In our simple example, we had the two islands and then we established the tunnel. But do you do this by hand, or do you basically peer with all the other islands? So that's really cumbersome. So setting up the tunnels, you can imagine, so you want to talk to all the other IPv6 islands, how to do this. So, problem. So you cannot do this via manual configuration. So that was the beginning of all this. This IPv6 to transition. There are some more tunneling ideas that isolated IPv6 islands connect in an IPv4 world, and how you avoid this manual configuration. There are RFCs for it with automatic, this point-to-multipoint tunnels, and so that you don't have to do this by hand. And this also talks about how we assign IPv6 prefixes to IPv4 addresses. And so the sender will use IPv6, and then the routers then knows, depending on a special prefix, we now encapsulate the IPv4 address in this. So you see there are many ways how we can somehow live together, that, okay, we embed the version 4 address into this special version 6 packet with a special prefix, etc. But to be honest, yes, these are all migration technologies. So if they have to be used, yes, use them, but it's much, much better just go clean IPv6. So what I showed you, we are not there yet. Some countries only 1% of IPv6. That's not a lot. And if you look at your router at home, quite often you see, yes, you have an IPv6 address, but preferred for whatever DNS is still version 4. So there are some more techniques, just to give you a bit more info, that uses network address translation. I will give you later in the course some more info about network address translation. The core idea was in the beginning, we don't have IP version 4 addresses anymore. Can we do something? Why not letting all the clients use private addresses, then do some translations? I will come back to this. But here it's a question of how to perform the transition to version 6. And there are certain extensions, what can be done there, and how we actually can perform this transition. So we can translate 6 to 4. We can translate back from 4 to 6. So one way of doing, I showed you, was a tunnel. A tunnel has had the big advantage, we connect the IPv6 islands and nothing changes. We still have the same packet. But imagine we have to connect all the IPv6 islands. With the help of this translation, we don't need tunnels. So again, we have our islands here. We have islands. We don't set up a tunnel, but we have routers here that speak 4 and 6, and they translate the packets. Then we don't need a tunnel, so we can connect to any of these islands. We have our headers, and now not using a tunnel means we create real IPv4 packets, so we drop the IPv6 header. We create, by translation, IPv4 header, and then we create back an IPv6 header. Big advantage here is, well, no tunneling. And tunneling requires, you have to know where to establish the tunnel, you have to set up the tunnels, etc. Here, no tunneling, but we use the classical IPv4 routing to transport it. But we will drop certain characteristics, so header fields are not 100% compatible. So if we, for example, want to use flow labels, there are no flow labels on version 4. So there are problems here, but that's also one way of doing it. So I know these are now just tipping to some of the technologies. So what you can do, you could tunnel, you could translate, but in the end, you notice these are not ideal situations. So yes, we can migrate, and a typical way of doing so is we go for dual stack in the devices, so that if required, we can use version 4, but if we can use version 6, perfect, go for version 6. That's the simplest way of doing. But there are some migration steps in between. They say, okay, we can do version 6. Oh, there are some other islands doing version 6. Now we can set up a tunnel there that tunnels through this old world of version 4, or we can exchange the headers, like shown here. But these are all technologies that are not perfect. So it's much better to have a clean IPv6 world. So what you have to remember is not the details of this. They serve only as pointers to literature that you on your own, if interested or if required, dig deeper into how this is then in detail done. But you should know as what is needed to switch over. We know we cannot simply say drop version 4, now immediately go to version 6. So what are the problems today, still many years after introduction of version 6, and what different strategies do we have for the migration? So why is it still needed? We have IPv6 on all systems. They're all operating systems, mobile devices, fixed devices, everything. They all support IPv6, but still we need migration. Why?